Good Monday chemistry class. Hope you guys are doing well. Today we're going to be talking about half-lives and how exactly we figure out what the half-life is of a certain element, radioactive element. So we're going to start from the current slide here. Now the first thing you need to know, and hopefully you guys remember this from last time I talked, at the very end of the video we talked about rates of decay and half-lives. And so right here it says nuclides. Now, the first thing we need to know is our radionuclides, and they have different stabilities and decay at different rates. So every single radioactive material that we're talking about decays at a different rate. They're not the same at all. And so we're going to talk about how to actually figure it out. So if they're all different, when is this one going to change into another element compared to another one? So here is our equation, and oh boy, it might look like a doozy, but trust me, it will all make sense. We're going to have a lot of work to do with this, and this is probably going to take up the bulk of this week, us going through problems on how to solve these different half-life formulas. So, right here, just to read it off for you, let me just pull out my laser pointer real quick. Bam. Now it says you have log right here. Log is a function in the calculator, in case you didn't know. And then you have A naught. So this stands for A naught. Anytime you see this subscript 0, that means not. At the bottom this is A, and we'll get into what it means. You can read it already, but anyway, and this is equal to K. This K changes. T, this T changes, and then finally this number. This number is always the same. So that's good. We've already got something going for us. Now, what is A? A is the amount of decaying sample remaining at the time of T. And so, right here, this A is how much of the sample we have left in its original form. A naught was the amount of sample present at the beginning of when we started looking at it. Now, K is interesting, and K is the rate constant. This changes for every single radionuclide. We're going to talk about cobalt-60 later on, and we're going to go over that constant for that one there, and we'll see how that works here. And then finally we have T for time. And so that time changes based on what you are doing. So that's our different things here. There's also this formula as well that you can use here, and it's log n naught over n is equal to kt over 2.303. Now, for the most part, I do want you to write this down, but I don't see me giving out too much work with this formula. Most of the time, it's the other formula that I showed you first. So let's keep on going here. So your half-life is described as the amount of energy, or amount of time, the amount of time required for half of the original sample to decay. And so, let's say we started out time 0, it'd probably be up here somewhere, and then time 5. Let's say this is like years. Years would be more realistic for a lot of these things here, and so by about 2.5 years or so, you'd have 100 of that sample left. And then right around 4 years, you'd only have about 50 whatever of that sample left. Maybe grams, maybe micrograms. And then around the 6-year mark, look over here, notice, you only have about 25 grams of that left. Then we get to here, and every time this happens, what you're actually doing is 100 to 50, 50 to 25, 25 to 12.5, 12.5 to 6.25, 6.25 to 3.1. Anyway, the point is, that's what's going on here, and you can see that it makes this curve. And that's what half-lives do. As each half-life comes by, the amount of what you started with halves, and it changes into something else. So you can actually track it this way. After the first half-life, you can see here, let's say there was 200 at the beginning. The first half-life, let's say, is around 2 years, right? So you have 100 left of the original product, and then you also have 100 of the daughter product here. And the parent is the word we use for the original sample, and the daughter is the word we use for what comes from the original sample, what it changes into. And it makes sense because daughters come from parents. I should know, I have a child right now. A little girl, a little cutie. And it's cool to see here, but these two graphs are inverses of each other. Now, over enough time, you will see basically 0 of the parent cell, and it will all basically be the daughter cell. But you'll never get to absolutely 0 of the parent cell, and you'll never get to absolutely 0 of the daughter cell. That's never going to happen. It's just, theoretically, if you had an extremely long amount of time, you could get to it, but there will always be like a small amount. And that's kind of the way half-lives work. You know, if you took half of something and you kept taking half of it, you can keep taking half of something forever. That's a crazy mind thing to think about, but it's true. Let's keep on going here. Now, this is your half-life formula for the most part. Now, T 1/2, this is half-life. That's all this means here. Okay? Now, your half-life is equal to ln2. Now, ln2 gets simplified over here to 0.693. You can actually do this on your calculator. If you put in ln2, you'll get this number. So this number stays the same. And that is equal, well, this divided by k, right? So, to find the k of any element that is radioactive, what you have to do is you have to put that number over the half-life, and that's how you figure it out. So, half-life is just a part of that formula. You have to do all of that, what I showed you before, to get this K right here. Here's your example. So I told you you're talking about cobalt-60, and it says cobalt-60 decays with the emission of beta particles and gamma rays. That's not important for us in this example, just good to know. With a half-life of 5.27 years. That's important. Make sure to underline that. How much of a 3.42 microgram of cobalt-60 will remain after 30 years. Alright, so we've been given everything we need to actually figure out our decay. So the first thing you do is you figure out what K is. And K is equal to this number. Remember, this number is very important. Make sure you keep that around. Divided by the half-life. And we see the half-life right here is 5.27. So that's how we figure out what K is, which equals this number right here. And the unit, you don't really have to be too concerned about it, but if you put it in your calculators, you should get this, or something that looks very similar to this. From there, we break out our formula. Remember this guy here? This is what we're going to use to find out the decay. Log, open bracket, A0 over A, close bracket, is equal to KT divided by 2.303. And if you want to know where I got that from, it's from a couple slides back. And now we start plugging in the numbers. And so our A0, or our amount at the beginning, was given to us here. So that's where this comes from. How much of this? Boop, you drop that into there because that's our sample at the original. And then it's equal to, we found our K already, so we just put K up here. We know our time is 30 years. And divided by 2.303. Now this is just some algebra. All of this, when you work it out, will give you this number right here, 1.713. Now, here's where things get a bit iffy. How do you even solve for A? Now, if you guys have been paying attention in your math class, you will know that there are inverse functions. And basically what happens with an inverse function is when you do that inverse function, it cancels out the other function. And so there is an inverse function, thankfully, for log. It's called antilog, and you take the antilog of both sides. Now, antilog is also known as this here. So you might find this symbol on your calculator, or you may find antilog. But I've seen this symbol more often here. And so this is just the problem restated. And what we did here is we just took this down here and we got the antilog of both sides. And so antilog and log cancel each other out is equal to the antilog of this. This will get you your log slashed away, 3.42 micrograms over A is equal to 10 to the power of 1.713. So that's what you would want to figure out here. Now you'd want to figure this out. And the next thing I do is actually going to show you what it is. And then they did 2 steps here. I would have did one step and did the other one, but for sake of space, I think it's better to do this here. And so 10 to the power of 1.713 is this number here, 51.6. You can try that in your calculator and make sure that comes out the way you want it to. And then we multiply both sides by A because we want to get rid of this A here. And now you guys should know what to do here. We have to divide now both sides by 51.6 to get A by itself. And so once you do that, you'll get your answer of A is equal to 0.0662 micrograms. All right. So today you are writing down notes. You are making sure you get all of this here. And I think I'm going to give you a small quizzes over some radioactive decay stuff just to help remind you of stuff that you've been doing before. But tomorrow we are going to be working on a worksheet all around this here. And so just like a lot of the other stuff we've talked about, it takes time. Now, some of you might have seen this and figured out exactly what was going on immediately. And you're going to do great. That's fantastic. But I am still going to work through this worksheet with you guys. And so tomorrow, Tuesday, you can expect to see a video of me with a worksheet. I'm going to work through a couple problems, and then I'm going to let you do the rest on your own. All right? So I hope you guys do well. I hope to see you guys on Tuesday. Hope you have a wonderful time, and goodbye.